All right. So I'd like to welcome everybody to the NAL First Thursday program. It is April 3rd. News and updates for today. The U of H Cougars are in the Final Four. The Rockets have finally clinched a playoff berth.
And sure enough, I found them on the floor. Sink. Oh, you found.
Everybody, please mute. Thank you. That's very helpful. Appreciate that. Anyways, let's see. We got the Cougars in the Final Four. We've got the Rockets with the playoff berth. And the Astros apparently left their bats at spring training camp. So somebody's going to have to go to Florida to find them. I'm Lisa Spence. I'm going to be your host for today. And just one more really quick announcement. Space Center Houston is looking for volunteers, and everybody in this organization, everybody in the room, everybody online has the requisite knowledge to be a volunteer for Space Center Houston. The deadline for applying to be a volunteer has been extended until tomorrow, April 4th. And if you have any questions, we do have Pete Hasbrook in the room today. So he will answer questions later about, he's been a long-time volunteer. Notice I didn't say old volunteer, long-time volunteer at Space Center Houston, so he can answer questions about the process and the kinds of things that they're looking for, things like that. Okay, so our speaker today is Dr. Stuart George. Dr. George is a physicist working in the Space Radiation Analysis Group here at the Johnson Space Center. His research is focused on space radiation protection and specifically on the development of hybrid pixel radiation detectors to protect NASA crew during human spaceflight. He's going to have to train all this. Dr. George has worked on a large variety of flight instruments during his career at NASA. Recent highlights include serving as a principal investigator for radiation measurements during the recent Polaris Dawn mission, instrument science lead for the Hera detector, and he's going to have to define Hera, on the Artemis 1 and LETS detector on BioSentinel. He also serves as the PI for the Compact Electron Spectrometer, a space weather early warning instrument funded by NASA, the NASA Development and Advancement of Lunar Instrumentation Program. His research has been published in Nature and featured in a variety of media outlets, including CNN, Reuters, and ABC Australia. Prior to working for NASA, Dr. George held a Marie Curie Fellowship at CERN and completed degrees at the University of Wollongong, which is in Australia, and University of Sheffield in the UK. His talk today will focus on the variety of technologies that have been and are being deployed to protect human space travelers from the harmful effects of radiation, which is one of the key hazards of human spaceflight. So at this time, we are going to start his presentation and bring Dr. George.
Lisa, you might push the mic.
Oh, you don't need to hear me.
Dan said I just comment.
Okay.
So that one's the web browser. Should have it. That's the one last one. I believe it's the one that to the right of that. Yep. Nice. Because you know the engineer best.
He did. He- 3 weeks ago.
Like I said, every once in a while.
Yeah, it is. It's every week.
Turn it over to you.
All right then. So thank you very much for the opportunity to speak here and that very nice introduction. I'm quite happy to take questions throughout the talk. So, you know, if you want to interrupt me, just holler at me. That's fine. And so, yeah, I'm here to talk about some of the radiation measurements we've done on Artemis 1 and in deep space, and also what we're sort of planning to do to keep crews safe from some of the hazards of space radiation for Artemis. I have this huge list of people here who have at some point or other contributed to this work, and I'm sure that it's incomplete. Yeah, lots of people, lots of different places. And I just wanted to talk a little bit more about the group that I work for, which is the Space Radiation Analysis Group. And I've this is a term I borrowed from meteorology, sort of O to R to O, operations to research to operations, right? So we are the group at Johnson Space Center that is responsible for the protection of crew from radiation. There's been a group at JSC doing this kind of work since the Apollo era, actually slightly before. And the shape and exact composition of that group has evolved since then, but there's been this continual thread of understanding radiation, sitting in a mission control back room to support various flights, and development of hardware. And so I've sort of said where, you know, the normal term that you find in meteorology is research to operations to research, and I've kind of flipped it around here because we have this operational focus, which is protecting the crew, but we also do some research activities which are really based on sort of developing the tools and the capabilities we need to go from a sort of LEO environment out towards these Artemis, you know, towards the Artemis program and these lunar missions, and then further out into the solar system. And so in this talk, I'm going to talk about, I'm going to sort of introduce the space radiation environment, talk about some of the measurements we do and we've done, and talk about how we're going to protect crew in the future in the Artemis program. And I'm going to do this really, I'm going to talk about these environments through reference to some of the measurements we've done on Artemis 1 in particular, and on a deep space free-flying satellite called BioSentinel as well, and really to illustrate the differences between a heavily shielded protected spacecraft like Orion and a much less shielded unprotected scientific probe, which is much more like a spacesuit or something like that. So I guess the first thing I should probably talk about is why we're even interested in radiation in space. And the answer is because there's a reasonable amount of it compared to terrestrial exposure. And of course, you know, humans are not really adapted to living in any sort of environment with radiation in it. And so I got some example numbers here. On ISS, for example, we get about half a milligray-ish a day of radiation, and on the ground it's, you know, more like 3 milligrays a year. And I have some more charts in just a second on this. And in addition, I mean, something that's quite interesting about space radiation is that most of this radiation that people are exposed to is so-called galactic cosmic rays. These are high energy particles from outside of our solar system, and these have these contain sort of heavy ions, so things like helium and carbon and iron. And these heavy ions have different biological effects to most of our ground data on human effects of radiation, which is mostly from gamma rays and mostly from the Hiroshima and Nagasaki bomb survivors. So the fields that we really know, you know, what they do in people are different to some of these space radiation fields. And the other thing we, of course, worry about much more with Artemis than with ISS and you know, shuttle missions is exposure to space weather. And what we're really worried about there, you know, before I was talking about long-term chronic exposures where you slowly build up a cancer risk over time, you know, with your time in space. With a chronic exposure, with a solar particle event exposure, the big concern is more that you get enough radiation in a short space of time, you get some sort of acute effect, you get radiation sickness. And so, you know, our events that we've kind of seen in the space measurement here in the last 50 years have the potential, of course, kind of moderate acute radiation syndrome, enough to sort of have impacts on crew. And if we look back in the historical record and try and reconstruct what some of the great space weather events of the past might look like, there is certainly the potential to cause mission-threatening exposures. And not necessarily, you know, exactly what that means is nebulous, but if people are very ill or very sick, you know, that's definitely a mission-threatening exposure. And so, you know, we want mitigating and understanding these is a pretty big goal of the Artemis program. And so I have this radiation dose chart here, which I've stolen from a webcomic called XKCD. I have my reference for it on the next slide. And the way this works is it starts on the left with small kind of everyday exposures, right? So right at the top, you can see eating one banana, right? So everyone sort of knows, it's popular science how that bananas are radioactive because they contain a small amount of potassium, and potassium has a small amount of potassium-40 in it, which is a little bit radioactive. And so that's why it's up there in that light blue, 0.1 microsieverts. And the way this works, then down the bottom, you've got sort of an airplane flight, a domestic airplane flight, and then that all gets squashed up into that little blue box on the top left of the green bit, right? And the point of this chart, of course, is that radiation exposures can cover many orders of magnitude, right? And then on this chart, we start having, for example, I've marked out a couple of reference spaceflight exposures here, right? So I've got sort of 1 day of ISS, 1 day of Artemis, one down there. The first day, the Polaris Dawn flight went up into the belt, so I've kind of got that down the bottom there. You know, here's your sort of reference 5-day deep space mission on the right. And if I go to the next slide, we then get out of the realm of kind of largish but routine exposures into what we consider quite large exposures. And there's the green chart kind of squashed down. And then we've got the Artemis 1 total dose up in the kind of top left there, the red bits. We've got our control limit for solar particle events pointed out there. And then in the bottom right, we've got what we think a large solar particle event, if you were to spend the entire period of it in a spacesuit, would look like in terms of exposure. You know, to be clear, that's not really a tenable scenario, right? Because large events have always gone on for many days, and it's not tenable for somebody to spend several days in a spacesuit without going back to a vehicle, realizing there's a solar particle event on, et cetera, right? But nevertheless, these numbers, 4 sievert, 5 sievert, they show up in the academic literature in what I think are very unrealistic scenarios, but I've sort of marked it out there to kind of show you, you know, if you were to be completely ignorant of such things, where you could go, okay? And I just have some nice pictures here about our radiation measurement hardware that we have. This is with Megan MacArthur in the US lab on ISS. And I've got a couple of different radiation instruments there. I've got the little USB stick thing at the top, is what we call a radiation environment monitor. The yellow box there is the RAD detector, which is a version of the RAD detector, is a ISS-specific version of an instrument that actually went to Mars on the Curiosity rover. And in the bottom right is a tech demo at the time about a HERA detector for the Orion spacecraft, which I'll talk about a bit later. So you can sort of see the HERA just sort of like that here. I also have another photo of this is Crew 7 with their holding their active dosimeter badges. These are little personal radiation monitoring badges that they will produce, and those track their exposure over time, so we know what their individual doses are. Again, in the US lab. And I have a photo of the Polaris Dawn crew here. And we could just about, I went searching through photos, looking for a photo of our instrument in Polaris Dawn, and I just caught a little tiny hint of purple peeking out between the seats there. And I think it was very good that we made it purple and not white. Yeah, there it is on Polaris Dawn. And I have a much better photo now of one we flew on, or is flying right now on Fram 2. And then here is a photo of the LETS instrument that we flew on Program Mission 1. As you may know, that was supposed to go to the moon, and instead it went to its fiery demise over Australia. But we still were able to measure the radiation environment on the way out to lunar distance and back again. So I have a bit of maths here, for which I apologize, but I thought I would, because I'm going to show some graphs of things in the next few slides. I thought I would just explain what some of these quantities are that I'm going to talk about. And so when a cosmic ray comes into you, it doesn't just like hit you and stop. It's more like a tiny bullet. It kind of goes and it kind of blazes a trail through your cells, right? And some of the more energetic cosmic rays will come in one end and will go out the other and keep on going. Some of the less energetic ones won't. And so we have this concept which is relevant to how much damage they do, called the linear energy transfer. And this is how much energy that the cosmic ray deposits divided by how much length it's deposited it over, okay? And so a particle with low linear energy transfer, you know, to use the bullet analogy, might be a small caliber round, and a particle with big linear energy transfer might be an artillery shell or something, right? Maybe I've taken this analogy too far, you sort of get the point. We also have some other numbers, the dose, which is just a straight energy imparted into a biological system per unit, or sensor per unit mass. And the dose equivalent, which is where we take the dose and then we weight it for what we expect the biological impact to be. So this thing, if this is bigger, it has more biological impact kind of per pound, per shot. This thing is, the dose is just how much is the easiest thing to measure. It's how much energy you impart per unit mass. And then this is actually how bad it is to the person, okay? And then we have this other concept of the quality factor, which is how bad the radiation field is for you pound per pound. And most of the quality factors we have from fields on Earth are 1, right? So for 1 unit of dose, the field is 1 bad for you, as it were. But in space, those quality factors can also be higher. So hopefully, as I start to show some results, it'll start to make a bit more sense. I thought I might just talk about this quality factor idea a little bit more. So I have a really nice, what I think is a nice illustration of the differences here between low LET and high LET radiation. And on the bottom, you can see a low LET particle coming through some DNA. And what it's doing is the little green and red dots are where it's interacting with the matter around it and potentially doing some damage. And if you have one of these low LET particles, most of the time, what we think that will do is that will come into your DNA and it will break one side of that double strand, okay? And what's really nice about DNA is, of course, you have a copy of that on the other side. And this happens, these single strand breaks, they happen in you all the time. There's, I think, tens of thousands will happen to everyone in this room every day. And you have mechanisms, you have little, cellular machinery that will climb up that DNA, say, oh, I've got a break. And it will say, what's on the other side? Oh, it's T, so I need to put A on the other side. That's right. And it always has the copy to repair itself based on, okay? Much more damaging, though, is if we get from the high LET radiation, which is in the top right here, where there's a much greater density of damage, where we don't just break the DNA on one side, but we break the DNA on both sides instead. And then you have to make up what was in the gap. Okay, so instead of being able to climb up and just say, okay, I've got my copy here, instead you have different mechanisms that take place. So you try and kind of glue the DNA back together, or your cellular machinery does, right? And when this happens, you can get mutations and you can get risk of cancer. And so this is how this mechanism, single strand breaks versus double strand breaks, is what's thought to be one of the main drivers behind radiation giving you cancer. And you can kind of see from this nice picture that if you've got a much higher density along your length of these interactions, you're much more likely to produce double strand breaks, and you're going to have a higher risk of cancer. And so this manifests itself in, I've got this graph here of linear energy transfer down the bottom and quality factor up here on the y-axis. And so as you go up in these density of ionizations, you start with this kind of quality factor of 1, and this is kind of based on cell experiments, or an average of cell experiments. And then as you kind of get above a threshold, you start really turning on the switch for these double strand breaks. And so pound for pound, you start having more and more DNA damage as you go up this LET curve. And then you can see on this graph on the bottom right, it kind of peaks at about 100. And after that, it comes down again. And you're like, well, why would it come down if it causes more double strand breaks, right? And the answer is that at that point, there's so much ionization density, you're not just damaging DNA, you're also having big risks of cooking other parts of the cell as well. And so you're not just potentially, you're not just damaging DNA, which can cause mutations, but you're also breaking the cell in general.
Is this instantaneous, or what's the time factor?
So these cellular repair mechanisms evolve over, the DNA repair is pretty fast. And then these different cellular repair mechanisms evolve over different periods of time. I think, for example, when your cells make the decision they're too damaged and they have to commit suicide in an orderly way, cells often will do that. I think the time process for that is about a day. And something that is interesting is that if you give people a lot of radiation and something in a short period of time, it seems like different processes can take over in terms of, especially on sort of the cell and organ level, right, than if you get this over a long period of time. So I presented a pretty high level kind of view of this, right? And biology is really complicated, right? You take cells and I'm glad I'm not a biologist, you take cells in a petri dish and they do one thing, and then you put them into an organ and they do another thing, right? Even though they're in principle the same cells, right? And then you put those organs into an organism and they do yet another thing. And of course, as you start upping the complexity, it becomes more and more difficult to study, right? So this is like I said, is a high level approach to some of the basic ideas for sort of radiation biology. And so the other thing I wanted to talk about was some of the environments, the radiation environments we have in space. And we have, I would say, really kind of three. We have that, like I alluded to earlier, we have the background cosmic ray environment, and I've just outlined sort of some of the important factors for radiation protection along the right there. And this stuff is always there. It's kind of omnipresent, and it sort of gives you a sort of chronic radiation risk. But there's not that much of it, relatively speaking. It builds up over time. And because it's very high energy, you can't really shield against it, but it's always there. It's not really influenced by many external factors. And really the main way that you protect against this is by trying to have a shorter mission, okay? Particle belts, these are like the Van Allen belts around the Earth. This is what I said, decreasing power law spectrum, right? So there's a lot of low energy stuff and not very much high energy stuff, okay? And if there's a lot of low energy stuff, you can shield that pretty well. In general, we think these particle belts are quite predictable. If you get a big geomagnetic storm from the sun blowing through, they can move around. We can mitigate against them by optimizing our trajectory to kind of, to not live in them. They're in defined places. And unless you're going to decide to go and live in the particle belts, your risk from them is generally chronic. And you'll see this with the Artemis measurements. And then we have solar particles from the sun. These are a lot like particle belts, except the sun makes them on a sort of quasi-random schedule. Again, shielding is really effective against them. They're not very predictable at all. There's a lot of effort trying to make them more predictable. And our mitigation is really to take crew and get them into a sheltered, more shielded environment. And the risks are, especially if you're poorly shielded and you don't do anything about them, that you get an acute exposure, which makes crew immediately, has effects on your mission. And so I think I've kind of sort of said this, why do we want to do these measurements in space? We want to keep track of the crew's radiation exposures, keep crew, this acronym ALARA can mean anything to anyone, but it means as low as reasonably achievable. And reasonably achievable is a big, and we want to keep crew away from really big exposures. So we have a career limit, which is 600 of those millisieverts that we were talking about a couple of slides ago, and a short-term limit from solar particles, which is 250 in less than 30 days. Okay. And then we have things we want to understand. We really want to understand vehicle shielding. We have heavily shielded vehicles and storm shelters we need to design, and this shielding really affects radiation. We have not great measurements outside of low Earth orbit. We have really good measurements in low Earth orbit, but outside of low Earth orbit, it's quite limited. And also we have lots of other people that are interested in biological effects of radiation, and we want to give them good numbers. And then finally, feeding through to operations, all these technologies help us to build better storm shelters for all the different vehicles in Artemis, and to plan, especially these long duration missions, which may be on the hook sooner than we all thought. We'll just have to see, right? And so I wanted to talk about, this is the kind of technology that we use in space. This is the one, the technology that I really know about and that we've used to design a lot of the recent radiation instruments. It's called TimePix, and it's a 256 by 256 array of little individual radiation detectors in what's called a hybrid pixel detector. It's about the size of my sort of fingernail. And it can do all sorts of nice things. And really the salient thing about it is, if you look at this, there's a diagram of it and stuff like that. But if you look at this plot, this is showing measurements with a TimePix of individual radiation particles of increasing linear energy transfer, like I was talking about before, right? And as you move from left to right, you get more and more biologically effective. And what we can see is we can actually see this structure. So I should actually explain what this is, right? This is kind of like a camera. This is the X direction in the camera. This is the Y direction in the camera, and then the color is how much energy we had deposited, like in the the pixels of the camera. Okay, and so this is really just like this radiation is kind of traversing the sensor here. This is doing exactly the same thing when it is traversing cells. Okay, and so you can sort of see in these, and you can see these ones on the right look much more intimidating, right, than the ones on the left. And these are the pound for pound heavy hitters, which are quite rare compared to these sort of lightweight things here on the left. And this technology, one of the things for building practical instruments is really nice about it, is that all of the digital, all of the analog electronics, electronics is very difficult, and especially for space, is integrated into this ASIC on the pixel detector. And so our job as engineers, trying to build this into a space-flight radiation instrument that has to be shaken, it has to be cooked, and so on and so forth in order to be accepted into a vehicle, and then it has to work for several, for a long time, is much more simplified by using something like this, which is kind of a ready-made solution almost. And what's nice about this particular technology, this is like a technology spin-off from particle physics actually, is people are using it for all sorts of other measurements, especially in medical imaging. And so it has commercial supply chains. It's actually not, other bits of our radiation detectors are expensive, but this actually isn't so bad, even though it's the heart of the whole organization or the whole thing. And so we've taken one of those TimePix hybrid pixel detectors, and we've integrated it into this instrument called the HERA. And HERA, we use these acronyms all the time, right? But all these names, but HERA stands for Hybrid Electronic Radiation Assessor. I think the naming of this thing involves local school children or something, and it effectively takes one of those little detectors, implements all of the circuitry needed to read it out, power it, and take those complicated pictures and reduce them down to a few numbers, and also contains power supplies and things like this, right? And so it's taken that technology and reduced it into a space-ready instrument that can go on a spacecraft. And And there was a lot of work obviously done to sort of make this, especially with the sort of data reduction to support a deep space environment. And in the end, we have we built some of these for Artemis 1, and then we built a fleet of these to support Artemis 2, 3, 4, 5, and so on and so forth.
I have a question.
Mm-hmm.
So it sounds like you got this technology from particle science out in the world, from medical stuff.
Yeah.
And then we're modifying it or miniaturizing it or whatever. Are we then coordinating and feeding that in as a benefit back to the medical community? Is it?
Yeah, so I mean, so specifically, if you want a little bit more of that story, so this, when you have a particle accelerator, you know, they smack particles into each other and they see what comes out, right? And one of the things you want to do is right in the center of those kind of experiments where they see what is coming out, you need a detector that can measure a lot of different things all at the same time. And because these have the pixels, they're really good at that. And so this technology was originally developed at CERN to support the Large Hadron Collider experiments. And then at CERN, there was a group formed called the MEDIPIX collaboration that wanted to take this technology and they were looking at it thinking, wow, this is really useful, and make it available for medical commercialization of drug uses. And then we kind of got a hold of it through a researcher at the University of Houston called Dr. Larry Pinsky, or Professor Larry Pinsky, right, who kind of brought it to this attention. We did demos of it on the space station, and then worked to develop it into these instruments. And so the MEDIPIX collaboration is still an ongoing thing, producing new detectors. And we've been feeding back some of our feedback on what we need to be a good charged particle detector back to this MEDIPIX collaboration. And that we still participate in that. We still go to some of these meetings. I think somebody's probably talking. Somebody's got a hot mic, right? Well, I'll leave it alone for now. And so that's been a good ongoing relationship, right, with them. Okay. Anyway.
Yes. I have a follow-on question to that, if I might, and perhaps your comment. Can you hear me?
Yes, I can hear you.
Yeah, I assume you're familiar with Frank Cucinato and the Marie experiments. And
Yes.
I've used some of this data in my own research. So, I mean, the first question that comes to mind is there's a chart that Cucinato developed at JSC about the risk of X-rays and various things compared to a ISS day and a human Mars mission. And I guess the conclusion was that I have the chart if you want it, that a Mars mission would increase the chance of probability of cancer by about 10% of the crew, and it would be a single mission. In other words, you get enough of a radiation dose, there wouldn't be any more. So that's kind of a famous chart that I use in a lot of presentations. But more than that, there's also data that I'm wondering if you're connected with, because it's funny enough, there's a show on Netflix right now called The Bomb and How the Cold War Started. And part of it involves interviewing survivors of Hiroshima and Nagasaki. And when you watch this, it's really unbelievable. There are some people who are within 10 kilometers of the blast who actually survived into their 90s, and they're being interviewed. And you know, it seems to me there's a data set of people that could really contribute to this, because these are people who are exposed to the worst kinds of radiation yet survived into their 90s. So I'm wondering if you're aware of, or there's any initiative to actually study these people, because there's enough of them you might conclude some of the stuff, as opposed to looking at individual cells, you'd be looking at humans. So, and the last thing I wanted to say is, as I'm sure you know, this is a very controversial subject. And Robert Zubrin, who I'm sure many people are familiar with, the case for Mars and other stuff, has done some independent research and published something called the radiation showstopper. It's not a problem. And it has to do with view factors. And this is a Mars mission we're talking about, and all the things that you can do to shield. So that's a lot of stuff I've just given you in a short period of time, but I'd be interested in your commenting on any of them.
Yeah, I'll work through these. Let me see. So number one, I'm not familiar with the chart you're on about. The 10% risk of, yeah, that's 10% risk of cancer for Mars is about right. It depends on exactly how you do the mission, but that's kind of the assumption, right? Like, you know, I sort of talk about this towards the end of my slides, but yeah, if you look at Mars, it's a 2-year round trip. The doses are somewhere between 600 millisievert and 1 whole sievert. The cancer risk per sievert is about 10%, of which about half those cancers are in principle lethal, and half those cancers you just have people living with the side effects of cancer treatment instead, which is also not great. I think so that number is about accurate, and that's sort of from that long-term exposure.
I have the chart up if you want to. I don't know if I can screen share from my end. I have the chart up here. I can
Little
send
bit-
it to you by email if it's better. But
Yeah.
Cucinato is a well-known guy, and it was the results
Yes.
of some Marie stuff.
I'm aware of Frank's work. So he was here, right, before he moved on
Yes,
to,
he certainly was.
yeah.
Yeah, it's close.
So, I mean, in fact, we still, you know, for NASA astronaut cancer risk, we still use the NASA space, you know, the space cancer model that Frank developed, right? Moving on to, I think the second topic was the A-bomb survivors. So the A-bomb survivors are the gold standard database for human effects of radiation, and they have been studied extensively throughout the last 6 years. And one of the the really good things done after Hiroshima and Nagasaki was there was this great effort to track where these people were at the time of the atomic bomb detonations and attempt to estimate what exposures they got. And then the people fastidiously followed those people through their lives. And that is really how we know as much as we do about the human effects of radiation, at least if you get those exposures all in one go like they did at Hiroshima and Nagasaki. But the one thing I will say about space radiation is that the kinds of radiation you have in space are qualitatively different to what the Hiroshima and Nagasaki exposures, you know, survivors were exposed to. And so there's only so far you can sort of take, that's one of the challenges, it's only so far you can take that translation, right? But for sure, almost everything we really know about the effects of radiation to the human, to a normal human, is from that data set. We have nothing
Let me
else.
let me just say one more thing about that. What I found very interesting about it was that when these survivors told their tales, some of them attributed it to what happened during the initial blast, what they were pinned under. They were pinned under a desk. They were pinned in a certain place. And my question really is, has any effort been looked at to see what the conditions were at the time of the blast to correlate with their survival? That's really to give an indicator of what really would work.
Terry, thanks for your input. You're a little bit outside the scope of our speakers' real.
Okay, sure.
So if we could let him go ahead and finish his presentation, that would be really helpful. Thank you.
Yeah. Okay. So anyway, here's a nice picture of the Artemis 1 launch on November 22nd. And from a radiation point of view, this is what Artemis 1 looked like. So the vehicle took off at 6:47 in the morning, and then you can sort of see that's number 1, and then through number 2 and number 3, it transited the inner and then the outer particle belts of the Earth. So Earth has 2 particle belts. The inner belt contains mostly protons, which are much more biologically relevant, and the outer belt contains mostly electrons. Then Artemis 1 went out into the deep space, the interplanetary radiation environment, that is, where it's not protected by Earth's magnetic field anymore. Round the moon with 2 close approaches marked by 5 and 6, and then came back over the poles on the 11th of December, sometime later. And in so doing, it avoided the radiation belts on the way back by coming over the poles. But that wasn't done to avoid the radiation belts. That was done in order that it would land near San Diego in the daytime. Okay. So there was a lot of different radiation experiments done on Artemis 1. It was one of the main goals of the flight. And the crew of Artemis 1 actually, so up the top here we have this guy in orange, I think he was called Commander Campos. But what I'm mostly going to talk about is Helga and Zohar, and these are what's called radiation phantoms. So they're bioanthropomorphic phantoms that are supposed to be an accurate representation of a human from a radiation point of view. And in addition, there were various instruments, and they're kind of all marked out here. There were M42s, which were produced by the German Aerospace Institute, EADs, which were made by ESA, and then CADs, and the HERA detector, which are the NASA instruments. And what I should emphasize when I talk about these results is this is a plot of the vehicle shielding density and the cumulative, and how much shielding there is on the cumulative shielding on the y-axis. Is that Orion, I think, would be considered a heavily shielded vehicle. In many places on Orion, there's what we call 10 grams. So if you have aluminum, and the density of aluminum is about 2.7 grams per cubic centimeter, 10 grams or about 2 inches of real material between you and space. Right, so it's not really a pressure vessel. There's lots of stuff in space because Orion is relatively small, relatively heavy, and full of stuff. And all that stuff is radiation shielding. The crew is in the middle, right? And all that stuff is radiation shielding. And so Orion is pretty much as heavily shielded as an ISS module is. And I have some examples there. Okay, and so this is what we measured. I was talking about the dose rate. This is the simplest thing for the amount of radiation that there is. And I got all these different plots here, so I'll talk you through them. So let's start with A in the top left. So A shows the dose rate on the y-axis, and you can see that's a logarithmic scale, right? Going from 10 to the minus 2 micrograde per minute to 10 to the 3 for the first 5 hours of the mission. And so that first spike is when the vehicle went through the inner radiation belt. And so you can see we got a rather impressive radiation field for a short period of time as we went through that inner belt. And then that second, much smaller bump is when we went through the outer belt, through those electrons I was talking about. Then we went into deep space, and I just have in B and C, I have these long-term deep space dose rates. So you can see on the left there, we're going from 0.01 to 1,000. Right, and then we have the sort of deep space dose rates of about 0.3 on that scale, right, but going on for the whole period, measured by B and C by different kinds of radiation detector. And then for D and E, I have cumulative exposures instead. So instead of the exposures per minute, I have the exposures all added up. And so you can see in D, this is again just showing what's in A, but cumulative instead. And so you can see that the different detectors saw between about 1 and 3 milligray now over that sort of initial period of belt passes, most of it in the inner belt. And the differences there are attributable to the fact that those detectors were all shielded differently. And so you can see when you go through that inner belt, the shielding has a really big effect on how much exposure you get. Okay, but then E is now showing the long-term exposures, the long-term cumulative doses out in, over the next 3 or 4 weeks of the mission, okay? And you can see that those slopes are all about the same, right? And so you can clearly see that you have a big effect on these exposures in D from the shielding, but when you now look at these long-term measurements, right, the shielding is no longer affecting your dose from the background cosmic rays, okay? And then finally, something that's kind of fun, F and G is showing the close approaches to the moon. And when you approach the moon sits there and occupies about a third of the sky, and that blocks cosmic rays from that portion of the sky. So no better shield than a gigantic moon. So anyway, and those radiation phantoms, I have a nice picture of one, and then sort of the internal geometry it's supposed to sort of represent on the right. It's a woman, because women are have been shown to be more radiosensitive on average than men. Radiosensitivity tends to be a very competitive person. But on average, women tend to be more radiosensitive than men. And on the bottom, you can see, for example, a CT scan of one of these phantoms, so you can see the sort of the biological relevance of it. And then I've just got the doses during the belt pass. During the inner belt pass, the outer belt pass, and the cosmic ray part of the mission, to different parts of these phantoms, to the skin, to the lungs, the stomach, the spine, and their back. And what you can see is, again, it's that same story, that over the inner belt, you're getting big reductions just in between the front of your body and the back of your body due to your self-shielding now. But then when you get into that cosmic ray field, your exposure is about the same. Another thing I have some nice, this is what I call the LET measurements. So this is those, how pound for pound biologically effective this stuff is, right? So you can see the inner belt is like that yellow curve and it's more off towards this is the amount of stuff on the y-axis and how bad it is for you effectively on the x-axis, right? And so you can see during the inner belt, most of the stuff is off on the left, right? So those inner belt particles, there's lots of them, but individually they're not that bad for you, right? And then for the outer belt, the extra contributions on the left as well. And then when you get on the GCR, you can see we have this tail that goes off to very high LETs. And then I just have a picture here on the right of what the individual particle tracks. This is what is going through your cells many times every second in the case of this look like. And so you can see we have this kind of prevailing, you know, these individual little streaks and going in kind of the same direction because the belts are quite directional. During the outer belt, it looks like this instead. These are the individual hits from the particles, and these are all X-rays. This is kind of fun actually. So the electrons don't get through the vehicle shielding, but the electrons still scatter around in the aluminum of the vehicle hull. That process makes X-rays. It's the same way an X-ray generator works actually. And those X-rays are getting into the vehicle and they're exposing the crew to a small amount of X-rays, relatively speaking, even if it doesn't look like it's that small. And then this is these galactic cosmic rays. This is the long period emission. And you can see like up in the top there now, we have some of these heavy hitters, these things that are coming in and being more biologically effective. Okay. And then I have all this nice table of everything we measured. And really the conclusion can kind of be seen here, right? That the inner belt, if we look at it, one of these sensors in millisieverts, despite being a very impressive thing to go through, is about 1.8 millisieverts over the whole mission. And then the GCR, the cosmic ray exposure, is about 25 millisieverts. So it's spending all that time, spending 25 days in that GCR field is much, you know, more overall detrimental to you than spending 20 minutes going through the belts, right? And that's kind of the story I sort of want to tell about the Van Allen belts, right? And you can see that sort of on the left and for the other two sensors as well. And what's interesting about these GCR dose rates, of course, is these measurements are directly applicable to a vehicle that is, for example, going on to, if you took an Orion and you were able to take that to Mars, this would be the same kind of dose rate all the way out, right, as you sort of did this, okay? Let me look at how we're doing for time. Okay, so another thing we measured that was quite fun is as we went through the belt, the vehicle spun. And remember I showed you before that those, that radiation field was all kind of in the same direction. In that picture I showed of the inner belt, well, something we saw is as the vehicle spun, we got this temporary dip that's shown in, the spin is shown in A, and the temporary dip is shown in B. That's the black line. You can see that dip on the right there. You got a temporary dip in the radiation dose rates. And we think this was kind of interesting and sort of unexpected. And so as Orion was going through the belts, it rotated to do its translunar injection burn. And as it did that, we think it rotated the ICPS stage into the path of the radiation, causing this dip in the shielding. And then it kept rotating, or this dip in the radiation because of more shielding. Then it kept rotated out of it, and then they burned to the moon. And I have some, this is the measurements of the angles of the particles we measured with the sensor down the bottom left. So this is kind of interesting. I think that the place that something like this is most relevant is some of the Artemis, for example, abort scenarios. It has them up in this high orbit where they're going through the belts a lot, trying to figure out what to do, but they're not doing a translunar injection burn. And so, for example, maybe we could, this is something we sort of sometimes talked about, but it's certainly not operationalized. Maybe we could have a preferred vehicle orientation or something in that scenario. Whether that's really tenable or not, I don't know. Yes?
Can you correlate that to Apollo?
So the Apollo measurements are more over the entire mission, but I think there are definitely other. So this AP9 proton flux, this is a sort of state-of-the-art radiation belt model. which is from scientific sensors that have kind of gone and explored the radiation belts. Okay, I mean, one of the things about the Apollo, so Apollo did have some pretty interesting radiation instrumentation on it. It was sort of a thinner vehicle, and obviously, you know, some things kind of remain the same in that Orion is quite similar in some ways to, you know, the Apollo program, but certainly our ability to measure and detect and characterize radiation has come a long way in the last 50 or 60 years. Okay.
So the nuclear particle detection system that we flew on Apollo then was a crude instrument compared to what you're using today.
I would say that, but then of course I would say that, wouldn't I? So yeah, no, I think, I mean, we have some of those. They're lovely detectors, especially for their time. And I mean, we have like a little museum of old instruments, sort of in our common area, and we have a couple of those detectors there. So
Yeah, when you have to mention museum in the same context, then it's crude.
So yeah, here's an example of taking these Artemis exposures out to a Mars mission, and we picked a couple of scenarios from the NASA design reference mission. You know, long stay, moderate trend. You know, these are different things that people came up with, and you can see we kind of go from at the absolute for this heavily shielded spacecraft, right? This small and dense spacecraft. We go from sort of half a sievert at the low end through to about 0.8 sieverts at the high end. And there are sort of, you know, this varies with sort of what the sun is doing at the time and things like this. But this is, I mean, everyone has these sort of calculations, and the numbers are all about the same for what people come up with, sort of half a sievert to a sievert depending, right? And seeing as it was already talked about, we would consider 600 millisieverts to be a 3% risk of exposure-induced death, right? So to back that out of it, like I said, that's about a 6% risk of about double that risk of getting cancer, and about half of those cancers being lethal, right? And half of those cancers, in principle, you know, you're having 5-year survival on them, right? For a 35-year-old female upper limit, and 35-year-old female is our sort of what we consider to be our sort of worst case from a biological risk perspective. Okay, this is maybe an interesting assumption actually, because of course one thing that's kind of fascinating on both Polaris Dawn and on Fram 2 is they've had now female astronauts that are quite a bit younger than 35. And so that's one of these things that we may have to think about a little bit in the future. But anyway, on an Artemis mission, we're very unlikely to hit this because of our relatively short mission length. And we have, for big solar particle events where we might drive this exposure, we have storm shelters. And so I'm going to diverge off a bit to talk about solar particle events with Biosentinel. And obviously I'm heading towards my hour, but I guess we're getting the questions as we go. So Biosentinel was a CubeSat designed by NASA Ames. It was also launched on Artemis 1, and it's a little bit distinguished in that it was one of the only CubeSats that was launched on Artemis 1 that worked. And it's now 55 to 60 million kilometers away, which I think is fantastic because it's a distance that can now be measured in light minutes. And it was originally intended as a radiation biology experiment. So Ames designed this very fancy radiation biology hardware based on rehydrating yeast at certain intervals where it had accumulated radiation damage and seeing how it grew. And then we had a radiation sensor on there to measure that radiation exposure that we designed. The biology, unfortunately, never worked. I think it spent too long in Florida. So I think that was maybe spending a year in Florida was worse for it than 6 months in deep space. But the particle detector worked fine. And we've been fortunate enough to be extended 3 times, once by Moon to Mars and now twice by heliophysics. And we're funded at least through September 2025 in principle. And so we're really the only particle detector where we are now in the heliosphere, and we're measuring dose, LET, all the things I talked about before, and also sort of photon spectra as well. And we get our data every week. And so compared to Orion is a heavily shielded vehicle, kind of a tank, and this thing is much more like a spacesuit. And I have a picture of it here compared to a sort of standard reference scientist. And you can see it's small, right? It's like this. It's small, and then the radiation detector is sort of like this, kind of on the side. And this is where it is now. I like that there's a plot with the sun and the earth and our thing in it. You can see them all in separate places. So you can see it's down the bottom right there in kind of grey if you can't quite make it out. Okay. And I have now some more graphs of the dose rate that we've measured as we go into what's called solar maximum. So the sun has a solar cycle which is 11 years long. Right now we're in what's called solar maximum. So the sun, when the sun is at the peak of its solar cycle, it's got lots of active magnetic regions and it's pumping out lots of solar wind. And that solar wind actually affects the low energy part of the cosmic rays in the heliosphere. And then when the sun, and then 11 years later, you know, the sun, or about 5 years after solar maximum, it'll go down into solar minimum. And there'll be a lot less solar wind, and the cosmic rays will proportionally kind of come up. Okay. And so this graph on the left is showing the dose rates kind of averaged over 6 hours, measured from 2022 through to 2025. And you can see kind of the baseline here kind of coming down. And then the other thing we see is all these spikes. And each spike is a solar particle event from the sun. It's the sun producing an energetic particle event that we're measuring. Okay, and now we can really measure these events because it's a small, lightly shielded spacecraft. And so we can see this background dose rate has come down to about 60% of what it was in November 2022. But in that time, we've also seen this increasing frequency of solar particle events, including 2 days now, which are greater than 50 milligray a day. This scale kind of, this scale here, which again, like I said, is logarithmic, it kind of envelops the range of, I think, what we think is reasonably possible with a solar particle event. So we haven't had anything capital B big, but we have had certainly several moderate ones, which have sort of delivered about 50 milligray a day or something like that, right? So if you recall Artemis, 50 milligray, if you recall the whole Artemis 1 mission was about 40 millisieverts, so it's about 20 milligray, 30 milligray, okay? And so, you know, you can see how much of an effect this shielding has had in terms of exposing you to these solar particle events. On the bottom there, I just have that same graph as the top, but now instead of a logarithmic scale, it's a linear scale to show that decrease of the background. Okay. Okay, so here's another one of these LET spectrum measurements, right, where, and you can see it has this long tail that goes out towards the right-hand side. And now the quality factor for the biosentinel when we're not measuring solar radiation is 4. So it's pound for pound, 4 times more effective than the same amount of radiation on Earth. And I just have a couple of examples of exposures from solar storms. What we've done here is looked at, I've taken 2 solar storms from May and June of 2024. May was, of course, the famous event where we had Aurora in Texas and all this. And the ISS is only exposed to solar storms really in the most northern and southern parts of its orbit. The rest of the time it's protected by the magnetic field. But you can still take the ISS exposure in those northern and southern parts and scale them out to what it would be like if the ISS was in free space. And this really shows you how much shielding affects these doses, right? Biosentinel saw 40 milligray in this time during the May storm, and if we take that ISS dose and extrapolate it out to free space, we end up with about 330 microgray, which is about 120 times smaller. Okay, so you'd much rather be in the ISS than you would be in the biosentinel during a solar storm, right? And so this is why when I start to talk about the importance of shelter, why shelter matters so much for solar particle events, is that we want to get you from the spacesuit scenario, which is more like biosentinel, or get a crew member from the spacesuit scenario to the storm shelter scenario, which is much more like ISS. Okay, and then just to sort of briefly talk about Earth's magnetic field, I have the June event, and the June event, the ISS the orbit was phased such that it was never in the parts of the Earth's orbit where it's magnetically unshielded, and so we basically measured nothing for that event, despite seeing 70 milligray out of the biosentinel. So we have a much more benign environment in low Earth orbit, even if we don't have all the shielding the space station offers as well. So let's go and talk about Artemis 2 a little bit. So there's the crew of Artemis 2. I think we're all familiar with how this mission will look. It's an Apollo 8-like mission. They're going to go out, they're going to go around the moon. I think they're going to spend a little bit longer. They're going to do a few orbits in low Earth orbit, and then they're going to come back. So the original, and I wanted to talk a little bit about the radiation shelter on Artemis 2 and kind of how that's evolved. So the radiation shelter that was originally sort of designed for the vehicle sort of looks like this. You have these are storage lockers in the bottom of the vehicle. And the idea was the crew would take all the supplies out of them, bungee them to the top, and then get in there. Okay, and that is, you know what, that is an excellent radiation shelter. It's about as good as it's possible to get in a vehicle like Orion. And I even have a video of it, which is, I'm not sure if I'm going to make this work or not, but
We did the test.
yeah, you can see, let's see if I click on this. So this might be a bit challenging, but basically they, it starts with them not there and they suddenly pop out from the storage lockers in this video. Maybe at the end I can find it because I know it's.
You'd have to pop out to get food or
Right.
stuff that you need and then pop back in.
Yeah.
Yep.
And one of the things we did on Artemis 1 was we used the belt measurements to try and validate the shelter worked, and we think we sort of, the belt's quite a lot like a large solar particle event, but only for 20 minutes, and we think we kind of succeeded with that. But now I have to show you what we think a worst case solar particle event looks like, and you're going to see some of the challenges with that shelter concept. And so this is the October 89 series of solar particle events, and what I'm showing here is the dose rate here, and then this is the time on the x-axis, and this was one big region that kind of came, rotated around the sun, and produced multiple individual large events. Okay, 1, 2, 3, right, and then a fourth smaller one at the end. And the thing that is immediately obvious about this is how long this goes on for, right? It started on October the 19th, 1989, and it was still going at sort of an appreciable level on sort of October the 27th. Okay, so it's probably not all that tenable to ask crew to go down into that thing, except if things are really dire, right? Yes.
So where does the shelter come in on this? Is it at a certain level or all?
Yeah, we have a dose rate threshold. We have a dose rate threshold after which the crew build a shelter, but I'm going to talk about that a little bit more because this concept has now sort of evolved from Artemis 1 to Artemis 2, and in response to these human factors concerns, right? And so we do this kind of calculation called ray trace analysis, where we look at the spacecraft, there's Orion, and we take points in the spacecraft and we shoot rays out from it to see how much material lies between the crew member or whoever's there and free space. Okay, and what you can see is that there's kind of a thin wall along here. That's the red area. Okay, and so the revised or the more practical storm shelter concept for Artemis 2 is to take all that material from the storage lockers, but instead of having the crew go down into them, we take that material from the storage lockers and we kind of peanut butter it against the walls. Okay, and that'll be pushed up against the walls with these bungee cords. And so now you have a scenario where the vehicle is much more usable, right? But we still get a reasonably good dose reduction compared to baseline. Okay. And so this is, and we still have, of course, the storage lockers in a slightly less efficacious form available if we encounter something particularly bad, particularly unlikely. Okay, and so I have some examples here for this October 1989 event of the exposures we expect in the nominal case. October 1989 is what we consider our sort of worst case event. Okay, in sort of the nominal case, the whole cabin shelter and then this storage bay as well on the left, right? So you can see we get, for the whole cabin shelter, we get about a 20% reduction. And the storage bay for this is a particularly hard event, particularly good at going through shielding, we get about a 40% reduction. But an event, this is actually 1972, not 82. But for that event, you can see we get 40 and 60% reductions in the dose exposure instead. And so to give you a bit of context for this, right? So we have these numbers are in milligray equivalent, so that's like the dose to your bone marrow. That's the point of that number, right? Because that's what really drives acute effects is bone marrow dose. And I think normally we would start to be worried about problems if this number got to about 500 or so, right? So we have a pretty reasonable factor of safety on this. Okay, I mean, it's not to say that it's not impossible that the sun can produce something very larger than these reference events. These are the biggest events of the space age, though, that we've seen. Okay.
And how predictable are those events?
Yeah, so to talk about the predictability, they're really not predictable at all. You can see there's an ugly looking region on the sun, and it's a bit like, but that's a bit like, you look at the National Hurricane Center map, and you know how before the hurricane forms, they have the X, right? And you're looking at the X, and you don't know what the X is 30% or something, right? They're not, it's like that. If you look at an ugly region on the sun, you can say, oh my gosh, that's a very ugly region, and then it trundles across the disk and does absolutely nothing. Another slightly less ugly looking region can produce a large solar storm. So this is the prediction and forecasting of space weather is a science that's really in its infancy. I hope it will come along a lot in the next few years. There's a lot of money being spent on this by NASA heliophysics, but it's definitely still a science in its infancy right now. To talk just sort of briefly about Artemis 3, now we're going to have crew land on the moon. And to just talk a little bit about our ConOps for Artemis 3. So the suits that Axiom is designing should have a radiation dosimeter kind of on the shoulder. This dosimeter is in principle, it should nominally be the same dosimeter that was originally designed for the XEMU project. That particular dosimeter got to PDR, and at least my understanding is that Axiom are just taking it wholesale and using it. The lunar lander is equipped with another one of our time-fixed space detectors, and that'll provide minute-wise dose rate measurement, and we can use that for solar particle event warning, as well as all of the satellite-based assets in Earth orbit. And then really for the way this will work essentially is, if we get a live solar particle event during EVA, we want to get the crew back fairly quickly. Something that's a bit interesting, right, is that we do want to have an acceptable level of dose for EVA where the crew can go outside, right? We don't want to be ultra conservative with this. We want, if there's a small solar particle event and we're going to be below this control dose, we want to be able to send the crew out to be able to do the things they need to do on Artemis 3, right? And if it's drizzling, if there's a little bit of rain, that's fine. But if there's a thunderstorm, we want to have them back inside. Okay, and so we're always trying to enable people, we're trying to protect crew, but not to be, ridiculously operationally conservative, right? It's all this sort of balance. And so we have this UVA control threshold for 10 milligrade. We might bust it if we have the wrong kind of event where the dose rate rises really fast, right? But we're still working this out in detail. Things may change a bit, but this is essentially what we're thinking for Artemis 3. And so if we move towards the future, I think a big capability that we'll want to develop is the ability not to respond to space weather events, but also to have predictions. So this is a project that I kind of work on called the Compact Electron Proton Spectrometer. And this CGI mock-up here, actually we've got a real one now that looks like this, but it supports nowcasting. So when an event starts at the sun, you get some precursor particles arrive to Earth before the main storm event, and we can measure those precursor particles, say, okay, this is going to be bad. Come on, guys, pack up, come back, right? And we can get a head start on that EVA return process with instruments like this. We also have a big effort to take in Space Radiation Group and with Goddard as well, to take some of the models people have built in academia for prediction of space weather and bring them into operations as part of this SEP scoreboard. And ultimately, I think, what we really want to end up is to have a capability that is Earth independent for Mars missions, right? Where you can even have something that's easy enough and predictable enough that you can have a crew member or a computer or something kind of looking at this data and being able to make these decisions autonomously. I'm kind of putting myself out of a job, but anyway. So I have this nice photo from October 2024 from Brookhaven in New York, where I was lucky enough to be up there at the NASA Space Radiation Laboratory doing measurements on the same day as I think the second biggest storm of the solar cycle. And we got an aurora display in New York, which was lovely. I sort of saw that things were happening. I walked outside and the sky was red. It was quite spectacular. So yeah, and that's really the end of my talk, and I'm quite happy to take some questions.
Very much. All right, first of all, do we have any questions in the room?
As it does my list.
So the Russians had a Matrushka experiment, I guess a torso, is that another one of these radiation
Phantoms.
kind of things?
Yes. Yeah, as I understand it, yeah. Was that on ISS or NEO?
I think they did it on Mir, but they also did it on ISS as well.
Yeah. So the Russians are obviously very interested in this kind of stuff as well.
One more. SpaceX is getting ready to launch a crew into a polar.
They're up there.
They're up there. They launched on Monday, and one of our radiation detectors is on there.
Okay.
Yeah.
What's your prediction for their exposure since they're above the Van Allen belts?
So then they are about, so the Van Allen belts get bad as you go up. So they're at about sort of ISS altitude. So the Van Allen belt passes for Fram. So SpaceX have flown 2 flights. They flew Polaris, right? And that went high into the Van Allen belts. And they got, in their first day when they were high, they got a dose equivalent to a few days on ISS, like a week or so on ISS, right? I talked about that at HRP a couple of weeks ago. On Fram, they're lower. It's more like the ISS orbit. So the Van Allen belt exposures aren't too bad. The thing that they're more at risk of is during the north and south polar parts of that orbit, is they're more at risk from solar particle events. And actually something that's interesting is as they launched into a small solar particle storm, and a pretty soft one, but I think we should see a small impact from that in our instrument. So I think you know, they're more susceptible in that kind of orbit to a large solar particle storm, much more so than on ISS. Not as much in free space, but of course the luxury that you have on a low Earth orbit mission is you can come back, especially in a space capsule, you can come back on demand, right? So I'm not privy to exactly what operational constraints, how SpaceX is doing that work, but they're really good people in their radiation group over there. We work with them on the storm shelter for HLS, for example. I'm sure that they've thought about this kind of scenario. Okay.
Do you expect them to share the data with them?
Yes, so for Polaris Dawn, so we were that data we've shared back with SpaceX, and we're also going to publish on it at some point in the near future. And we were funded by the Translational Research Institute for Space Health on that. Trish will be putting that database, that radiation data into a larger database called Expand, which is tracking all these private astronaut missions. And we'll do the same for Fran.
Okay, we have some questions in the chat, so I'm just going to read the first one. This is from Michael Bungo. We're studying radiation effects on atherosclerosis in crew members. What data is collected? This is data collected on the ISS, on the crew and crewed missions that we can access, like personal dosimeters, cabin data. And do they discriminate the types of radiation?
That's the biological equivalent. So I think you probably need to get in touch with me after this to answer that question. I mean, we obviously measure the individual crew members' exposure, but it's also their personal medical information, so we have to talk about data sharing separately, okay? But we certainly, it's certainly something, supplying doses for experiments is certainly something that we do, okay? But I think it's something we need to talk about. So if you send me an email, we can talk about it, okay? And then the cancer question.
Could you post your email then in the chat, please?
Yes. Yeah, we'll get it in there, Michael. So while he's typing his email in, the next question, is there any data that shows higher incidences of cancer? And it just went away in crew members. And I think you'd have to answer that as a yes or no question, right?
No, I can go into a little bit more detail because I can say that there isn't, and I can tell you why. So the problem with astronauts is that they're all really healthy. They're a super selected group of people who have been, they're not representative of the general population at all, right? You've got a selected group of people who are very, very healthy, who have tended to have healthy lifestyle habits when they were selected and have continued with those healthy lifestyle habits into, oh, you're doing much better than I am. So because of that, they would be expected to get cancer at a much lower baseline rate than the general population. So even if you had this increase in their risk from the radiation exposure, it would be very challenging to see it, especially with such a relatively small group of people. And the other thing I will say also is the only astronauts that have really gotten big radiation exposures, relatively speaking, have been the ISS cohort. The Apollo cohort did not really get a lot of radiation, and neither did the shuttle cohort. It's really been the ISS cohort with the long stays on station where we started to see these individual exposures go up. Okay, and obviously that's been more recent.
Okay, I have a couple of questions. On the chart where you showed the single strand versus double strand DNA breaks per LET, is that based on real data, or is that statistical or probabilistic?
You mean that thing?
Yeah.
Yeah, that's so that's a curve produced by the International Commission on Radiation Protection, and it's sort of an aggregate of studies, of biological studies, right? So it's a sort of general purpose curve, because that if you measure this LET and you want to predict what your biological kind of endpoint is, this is a general purpose curve based on sort of aggregations of animal and cell models and in the best judgment kind of the scientists on that committee. Okay.
Okay. So are some organs more susceptible than others for that type of DNA damage?
Yeah, in general, it's the fast dividing tissues. So it depends on, for long-term cancer risk, it's the tissues that divide fastest, which are generally the most high, the most susceptible. Okay, that's why we worry about kids. It's also why we worry about younger people more than older people, because younger people have a longer time to have their tissues divide and get cancer. And so, yeah, that's now for short exposures, it's a bit different, because then it's more about the efficacy at which you kind of kill cells and their ability to repair themselves. And different organs have strongly different capabilities to kind of recover from a large radiation dose. And so traditionally, the thing we worry about immediately is bone marrow for short-term exposures. Okay.
Yeah, I think this is just a question about familiarity with some of the other work that's being done.
So I mean, yeah, so the spacesuits are generally lightly shielded. So there's a question here about the protection offered by the spacesuits. And no, I mean, fundamentally to shield people from radiation, you need mass more than anything else, right? Mass is at a premium in spaceflight, and it's at even more of a premium in spacesuits, right? And so the spacesuits are not great for radiation exposure, and the primary mitigation we have for radiation exposure with spacesuits is monitoring the environment, being reflexive to what's happening and trying to pull people back if something bad happens into a more shielded environment. Okay. Yeah.
All right. Any other questions in the room? We're going to wrap it up here fairly quickly.
When did you begin your research?
Yeah.
20 years ago, 10, 15?
I have been doing this. I started working on pixel detectors for my PhD, which was in 2012. And I came over here. I did that. I started that in 2012. I came over here in 2016, working initially for a university. I had to have the foreign national badge, so they had to follow me on and off whenever I came onto campus. Then I got a green card a couple of years later, and they hired me as a contractor in 2018. And then I became a citizen like 2 years ago, and I then split over doing the civil servant last year. So yeah, that's my career in a nutshell.
So about 15 years.
Yeah, 13, 14, yeah. So.
Okay. All right. I want to thank you very much for that informative presentation. Thanks everybody online and in the room for coming out. Fortunately, it looks like some of our normal folks who come might have gotten blown away by the wind. It was really quite strong today. So just a couple more things. The recording for today's video will be available on the NAL website in a couple of days. Our next meeting is going to be Thursday, May 1st, so May Day. We should be live here in the Lone Star Room, so I'd like to encourage everybody to please join us for that particular presentation. And again, I want to remind everybody that Space Center Houston is looking for volunteers. They want your brain, they want your energy. Pete's nodding at me, so I'm saying good words for him. But if you're at all interested and you want to ask a question right now, Pete's in the room. He can entertain your questions. We also sent out an announcement about this volunteer opportunity from the NAL website a couple of days ago. So check your inbox. You should be able to see it there, or you should also be able to see it on the NAL website. So lots of information, but tomorrow is the deadline. So, you know, unlike filing your taxes, there is no extension, so don't wait. All right, thanks everybody.